Hi, I'm Alec Clark.
Hi, I'm Braden Stack.
And I'm Laura Leveren. The project our team is working on is called Lost Meadows. We built a tool that uses machine learning to locate lost meadows in the Cascade-Siskiyou bioregion. This allows land managers to identify possible meadows before doing costly field surveys. Why meadows matter? They aren't just beautiful, they play an important role in the ecosystem. They act as natural sponges, absorbing water during wet seasons and slowly releasing it through the dry summer months. They're biodiversity hotspots. There is flora and fauna in these meadows that you won't find anywhere else. In the Cascade Siskiyou bioregion, you'll find the cobra lily, the Oregon spotted frog, and over 120 butterfly species, including the rare Mardon skipper. Meadows also provide nesting habitat for songbirds like this little yellow warbler, and hunting grounds for birds of prey like the great gray owl. Finally, meadow soils store significant amounts of carbon, which can help combat rising greenhouse gas emissions. So, what's going wrong? As temperatures rise, more precipitation falls as rain instead of snow. Rain runs off fast. It doesn't recharge groundwater the way snowpack does. A farmer once told me rain is a paycheck, but snowpack is a savings account. Meadows that used to stay saturated through August are now drying out by June. Compounding this is beaver decline. They were trapped to near extinction for the fur trade, and their populations have never fully recovered. Beavers are important to meadow health. Their dams spread water laterally across floodplains, slowing it down and saturating the soil. Without that, streams cut deeper. Water tables drop to match the new channel elevation. The meadow soils above that level no longer stay saturated. Once that happens, the wetland grasses and sedges that define a meadow can't survive, and upland conifers and shrubs move in. The meadow function is gone. But here's the key: the landforms aren't. The geomorphology, the shape of the land, still shows where a meadow used to be, and that's exactly what our model is designed to find.
Now that Laura has introduced the problem, let's talk about how we're solving it. What did we build? We built an interactive Google Earth Engine web application that gives land managers the data visualizations they need to identify these lost meadows. Who can use lost meadows? We're going to focus in on one user group in specific, that being researchers. Pictured below, we have an example of two researchers we were working with, Hema and Jamie. They were very gracious to help us out with all the domain knowledge we needed to complete this project. And along with this, we hope to empower their research, giving them the data visualizations they need to improve their workflow.
Okay, now let's move on to our six features, which show a high level look at what we actually built. The core of the app is a map that scores every single pixel across our study area to identify lost meadows. Users can filter down to specific watersheds so it's not overwhelming, and every prediction comes with a confidence score so you can see the exact probability of an area being a meadow. On top of this, there are also condition sliders to adjust environmental conditions. The whole thing runs across all 119 watersheds in our study area, and we made sure it's easy to find by putting a direct link front and center on our website.
Now we're going to talk about tools and technologies. We have about six different categories we're going to talk to you all about today, starting out with the core platform, that being Google Earth Engine. We're utilizing this for two different aspects of our project. First, pulling the data from Google Earth Engine, that being the USGS 3DEP data, and then presenting our findings on the Google Earth Engine front end. Moving on to TAUDEM, this stands for Terrain Analysis using Digital Elevation Models. I like to think of this as a math suite. I know I don't like doing math. I bet a few of y'all out there don't like doing math. This makes it night and day easier with its plug and play functionality, allowing us to plug in our data and get the hydrological analysis and feature generation we need to complete the project. Moving on to Python ML stack, we're going to focus in on one library in specific, that being raster.io. This allows us to pragmatically interact with raster images. You may be wondering, what is a raster image? I like to think of it as a map where it has values and resolution. The values for each pixel is elevation measured in meters, and then the resolution is a 10 by 10 meter pixel. Moving on to XGBoost. This is a machine learning model that we are utilizing for our project. It is a tree-based model where it tries to learn from its previous mistakes. Moving on to Orca. This is the high-performance computing cluster that we are utilizing to enhance our workflow. This cut down our runtime on all 119 different watersheds from 20 hours to 30 minutes. It is also hosted by Portland State University, and they were very gracious to allow us to use it. Lastly, GitHub Pages is where we are hosting our website, allowing users to read all the information about our project and then launch the app directly from the website.
Now let's move on to our four-step pipeline. First, we export data for each watershed straight from Google Earth Engine down to our local machine. From there, we run it through a series of processing steps to pull out 28 different features about the landscape. These features include hydrological, terrain, and soil features. We then take all 28 of those features and combine them into one stacked raster. And then we use that to train our XGBoost model, which learns to look at those 28 feature values and decide, is this pixel a meadow or not? And then once the model is finally trained, we apply it to every pixel across all 119 watersheds and output a final probability raster, which we then send back up to Google Earth Engine and displays a color map, which Alec is now going to show you in his demo.
All right, so starting out, we can see this has been divided up into three different regions. Starting out on the left, we have all the different layer and map controls you can need to make sure you can find the meadows you're looking for. In the center, we have our probability layers. We have two we're going to be showcasing today. First being the watershed model, which has been trained and ran on the data within the specific watershed. And then the global model, which has been trained on all of the data within our research area and ran on that specific watershed. Moving on to the right, we have the pixel summary, which will give you all the summary statistics and map values for the pixel that you are selecting. Now we're going to let it run for a second. And we're going to start out with the watershed navigator in the top left. We're going to navigate to Big Butte Creek. It's going to auto pan in and select this watershed. And then we're going to engage that global model we were speaking about earlier. I'm going to pause here once it loads in. Awesome. So now that we can see the global model, we can see there's quite a few more predictions than the watershed level model. Moving on from here, we're going to disengage the global model. We're going to drop the opacity. And then we're going to select our NWI wetlands training labels. We're going to zoom in on this meadow here. As we can see, it's a PEM classified NWI wetland, which stands for active wet meadow. As we can see, it's pretty small. But once we engage this prediction layer, we can see it should be much larger. Next, we're going to click on a pixel and see its value. As we can see here on the right-hand side, it has a 99.2 likelihood of being a meadow based on the watershed model, and then a 98.3 based on the global model. The really cool thing about this meadow is that it's being ground-truthed already. We brought in some community partners earlier in the term to test out our app, and they actually went and checked out this meadow, and it's been designated as a restoration site that they will be going in and making it a bigger meadow.
Now we're going to look at some of the results of the data. The confusion matrix on the top left reflects a deliberate trade-off. We tuned the model to prioritize catching real meadows over avoiding false alarms. A false negative means a degraded meadow is never flagged for restoration. A false positive just means a land manager takes a closer look at a site that turns out to be fine. We'd rather send someone to check a patch of land than miss a meadow that needs help. The bar chart on the left bottom shows the per watershed model predicts over 57,000 hectares of Lost Meadows, while the global model predicts over 430,000 hectares of Lost Meadows. Per watershed models can be dominated by whatever meadow types are most common in their watershed. For example, a watershed with mostly lowland meadows may underpredict higher elevation ones. The global model sees the full range of meadow types across the bioregion, so it generalizes better. The feature importance chart on the right lists all 28 features. The top features are elevation variability and vertical drainage distance, which makes ecological sense. Meadows sit in flat, water-connected locations. The model has essentially learned to find the landscape signatures of meadows, even when the vegetation has been replaced by upland species.
Okay, so now let's move on to testing strategies. So the first thing we had to figure out was which machine learning algorithm to actually use. We ran XGBoost and Random Forest head-to-head across 3 wetland types. XGBoost performed better, so that's what we went with. We trained the model on around 100,000 samples per watershed. We tuned the hyperparameters, and we landed at around a 95% average accuracy across all 119 watersheds. Because of the large amounts of data processing we were doing, it was also important to have a test pipeline that runs end-to-end very quickly so we could validate that our pipeline works without having to wait a long time. And now let's move on to a division of labor. So the main thing I worked on for this project was the back-end pipeline and then the initial website draft.
The main thing I worked on was domain knowledge and data sourcing, the website data dashboard, and the climate overlay and slider feature.
The main things I worked on was the data acquisition via Google Earth Engine and the Google Earth Engine front end. Moving into conclusion and impact, we threw a lot of information at y'all today, so let's bring it full circle. With the ability to scale this research statewide to even nationwide, what would have taken researchers months of field work, this tool does in minutes. I'll leave y'all with our mission statement: restoring nature through technology. Thank you very much.